Okay, welcome back to the course. In this session, we're going to deal with permutation tests for multivariate pattern analysis, but not only for MVPA, because I'm only evaluating a little bit on the general principles of permutation tests. Just to clarify before I start, my name is Joram Soch, and I'm working at the Bernstein Center for Computational Neuroscience in Berlin. I'm here reusing slides of my former colleague, Carsten Ahlefeld, who is now a lecturer at City University of London and who has given this talk in the previous years, so I'm representing him today. Okay, fine. When you're reading the words permutation test, you may be wondering, why should I use a permutation test? What's wrong with my significance tests that I'm performing? Well, the significance tests that we are running and also Bayesian analyses, for example, make certain assumptions about the distribution of the data, especially about the noise in the data. And sometimes precise distributions are not known, especially in multivariate pattern analysis. And here a permutation test makes weaker assumptions. It doesn't make no assumptions, but it makes weaker assumptions about the distributions than such parametric tests. Secondly, permutation tests provide ways for exact inference. That is, they are perfectly controlling the type 1 error rate, and if the null hypothesis is true, it is rejected at most 5% of the time if you have chosen your significance level to be 0.05. Finally, the principles of permutation testing apply in the exact same way to univariate and multivariate analyses, as you will see later in the talk. In this talk, I'm not going to provide recipes for standard data analysis contexts or for your everyday life fMRI data analysis, but I'm more trying to explain the basic principles underlying permutation tests, especially the concept of exchangeability. So let's just start with a simple example. Let's assume we have acquired this very little data set, which consists of two groups, A and B, and we have acquired 3 data points in each group, A and B. So the question that we want to address now is there a mean difference between groups A and B? Well, what we could do is just calculate the means of A and B and take the difference. That's the mean difference. That's our test statistic, and in this case, it would be 2. Now the question, of course, is how significant is that difference? Is that difference statistically significant? If there's no mean difference between the groups A and B, values can be exchanged between conditions, because this wouldn't change the distribution of the relative distribution of the conditions. For example, we could exchange the 7 with the 6 and the 1 with the 9. And exchanging data points within conditions means that we are permuting the data, which leads to permuted data. So we have an original data set and we have a permuted data set. Again, we are calculating the very same test statistic from the permuted data, and in this case, it would be minus 0.267. Of course, what we want to do in the end is to compute the test statistic for all permutations. In this very small data set, we are in the lucky situation of being able to actually evaluate all the permutations. So test statistics are calculated from all sets of permuted data, and test statistics are being sorted in descending order, which provides us a way of attaching ranks to those test statistics. The original dataset, also referred to as the neutral permutation because it's being left unchanged, is of course part of the set and also has a rank. The rank of the original value determines statistical significance. So in this case, the mean difference would not be significant because if you've chosen a significance level of 0.05, only the top one value in a list of 20 values would be deemed statistically significant. Equivalently, a p-value can be computed, which just happens by dividing the rank of the test statistic computed from the original data by the number of total permutations, which in this case would be 0.25, far from being statistically significant. One can also implement a test for decrease. So instead of asking, is there an increase from A to B, is there a decrease from A to B, which in the end would just mean to reverse the difference, or equivalently use the negative test statistic, also not significant in this case. Finally, we can also run a two-sided test where we use the absolute value of the test statistics, because in this way the most extreme negative values and the most extreme positive values are all becoming extreme positive values. So for this little data set, which is probably not very surprising, there's neither a significant effect of increase nor a significant effect of decrease. And this is also does not depend on whether we are running a one-sided or a two-sided permutation test. So from this introductory example, we are already able to derive something like a formal procedure for a permutation test. What is required for a permutation test is that a certain data set has been acquired or simulated, that a test statistic can be calculated from this data set and from permuted versions of this data set, that there is a significance level alpha below which you want to consider effects to be statistically significant, and that there is a set of possible exchanges between data points. I will come to that. I will come to what that means in detail a little bit later. So, given that these requirements are met, the procedure is then as follows. First, we compute the test statistic T1 from the original data. Then we compute the test statistics Ti from all possible permutations, where I runs from 2 to the number of permutations. And this already signifies that I equals 1 is the neutral permutation corresponding to the original actually acquired dataset. In some cases, actually in a lot of cases, because this happens very fast, it's not possible to run all permutations. And in this case, one usually resorts to a random subset, randomly selected subset of the permutations, which is also called Monte Carlo sample. Next, we determine the rank of T1 within all test statistics Ti, which happens using this sum. So for each possible permutation, we are checking whether the test statistic Ti is larger than or equal to the test statistic computed from the original data. And if it is, we are adding up 1 to this sum, such that the whole sum would then give the rank of T1 within all the Ti's. Finally, we can calculate the p-value by dividing the rank by the number of total permutations. And if the p-value is smaller than or equal to the significance level, we reject the null hypothesis, accepting that there is a statistically significant effect. This test is exact, as I already hinted in the introduction, if alpha is a multiple of 1 over the number of permutations, and if there are no ties. Otherwise, the test is mildly conservative. Okay, in this formal procedure that I've just described, we have referred to a set of possible exchanges of data points. And this in turn refers to the concept of exchangeability. Formally, exchangeability can be understood as a situation in which we can exchange data points without changing the joint distribution of the entire dataset. This is perhaps best explained by looking at a few simple examples. So let's say we have just 2 data points or 2 random variables, x1 and x2, having this joint distribution. x1 and x2 are in this case independent from each other because there's no covariance between them. And they have the same marginal distribution, which means that they are independent samples from the same distribution, also called independent and identically distributed, which, by the way, is a special case of exchangeability. And independent samples from the same distribution can be exchanged. That is, if I'm here switching x1 and x2, the joint distribution stays the same. Independent samples from different distribution cannot be exchanged. So as you can see here, the mean of x2 is a little bit larger than the mean of x1, so that they don't have the same marginal distribution, which, if we switch x1 and x2 in this joint distribution, leads to a different joint distribution. Therefore, exchangeability does not hold. Please note that exchangeability refers to the null hypothesis. That is, if the null hypothesis is true, data points are exchangeable. On the other hand, if the null hypothesis is not true, exchangeability does not hold, because switching these two values does not preserve the joint distribution, as you can see when moving from here to here. Exchangeability can also be there if there is a dependency between variables, but this dependency has to be symmetric. For example, here we have a positive covariance between x1 and x2, but the marginal distributions of x1 and x2 are still the same. So exchangeability does hold and the joint distribution remains constant. Again, if there is a dependency, but this dependency is not symmetric because x2 has a larger mean than x1, the joint distribution changes when exchanging variables, and therefore this is not a case of exchangeability. You have to be very cautious because the null hypothesis may be wrong in rather unexpected ways. For example, this is the standard case of IID, independent and identically distributed data, which we have already looked at. But in the lower example here, x1 and x2 are independent from each other. They have the same mean, but they have different variance. And even though they x1 and x2 are independent from each other and have the same marginal mean, exchangeability does not hold because plausibly the joint distribution of x1 and x2 changes when they have different variances, and one is switching x1 and x2 here. So with these prerequisites, the formal procedure of a permutation test and the concept of exchangeability, we can now go and look at some basic test examples. The first one of this is the one which I've actually already used in the introduction. It's the univariate two-sample situation, where we assume that we have independent values sampled from two univariate distributions. And the null hypothesis is that the two samples come from the same distribution. In the independent and identically distributed, or IID case, values can be exchanged freely and arbitrarily between conditions. Upon exchanging those values, we would compute the difference of sample means, given by this formula, and this test statistic is sensitive to the difference in means, such that this procedure would be the permutation analog of the two-sample t-test. This can also be extended to a multivariate case, where we are now assuming that independent vectors, so vector-valued random variables, come from two multivariate distributions, and the null hypothesis analogously would be that the two samples come from the same multivariate distribution. In the IID case, vector values can again be exchanged freely, and after exchanging the values, we would train and test a classifier in a cross-validated fashion, which would give us a decoding accuracy as a test statistic. An example for this would be the classification of subject-specific patterns. For example, when comparing healthy controls with a patient cohort using structural MRI. And the individual entries of vectors would correspond to the structural MRI features, such as voxels or brain regions. Keep in mind that the entire vector is being exchanged between groups and not just individual or single values of this vector. There's a problem with accuracies, which is that sometimes decoding accuracies can only take very few possible values, because the number of possible values depends on the number of out-of-sample subjects or trials or runs being tested, and this can lead to ties, making permutation tests conservative. So now we're coming to a different situation. Again, we're considering two groups, A and B, but now we assume that two values from A and B are paired to each other in the sense that they are belonging to each other. So in this case, we would assume that paired values are sampled from two univariate distributions, and the null hypothesis would be that this is the same distribution. But now that there is a partial dependency, because these two values in a pair belong to each other, values can only be exchanged within pairs. We would then again compute the difference in sample means, and such that this is the permutation analog to the paired t-test. Here's the extension of this procedure to the multivariate situation, so the multivariate paired test. We would assume that paired vectors are sampled from two multivariate distributions. Again, because there's partial dependency, vectors can only be exchanged within pairs. We would train and test our classifier using cross-validation. And examples for this would be classification of condition-specific patterns across subjects, or classification of such patterns across runs within subject. So here, A and B are not two independent groups of people, but A and B might be experimental conditions. And because experimental condition is a repeated measure within subject, there's this partial dependency which prevents us from exchanging freely, but only allows us to exchange within pairs. If you are interested in an alternative to decoding accuracy, which is a very prevalent measure in machine learning based fMRI, you may have a look at this paper, which shows that multivariate samples can also be compared using significance tests. And this might actually be more powerful, because the test statistics in significance tests are not suffering from the problem of ties that accuracies are suffering from. These multivariate significance tests are not as well known as the univariate significance tests, but essentially they are based on the same principles of frequentist inference. So now I would like to point out some cases of limited exchangeability, that is, situations where exchangeability does not hold, or where exchangeability can only be applied in a very limited way. And a prime example for this is fMRI trials. So in an fMRI experiment, trials occur one after another, and there is a serial dependency in the functional MRI signal. So the first and the second are closely bound together, the second and the third and the fourth and the fifth, and so on, which can be visualized in this way. And because there is a serial dependency, exchanges of data points, like for example here, exchanging the data points denoted by A and B would completely disrupt this dependency structure as is shown on the lower visualization, which means that there is no exchangeability of values in fMRI time series. No matter if these are calculated on a scan-wise or a try-wise level. There is an exception to this, which consists in the following. So if these data points are attached to a try sequence, and this try sequence is itself randomized, what can be exchanged are, of course, the labels of the tries, because they are independent from each other from try to try. This, however, leads to a randomization test, which is not equivalent to a permutation test. So other than a permutation test, which makes assumptions about the distribution of the data, a randomization test makes assumptions about the distribution of the labels. So a disadvantage of this procedure would be that, strictly speaking, it only provides generalization to the space of all possible randomized designs, rather than generalization to the space of all datasets that could have been acquired. In some cases, there's a rather easy solution. So when an fMRI experiment is conducted in the form of separate runs or sessions, as it is becoming more and more common, then these runs or sessions can usually be considered to be independent from each other, and run-wise means or GLM estimates are often exchangeable, again, within runs, or within pairs if it's two runs. So in this case, run-wise classification may be a better alternative than running a randomization test. If you're looking to an alternative to classification in general, you may have a look at this paper, which describes cross-validated multivariate analysis of variance, which allows for arbitrary time series designs. So this may be more flexible than conventional decoding analyses, because the latter ones are usually restricted to very precise categorical classification contexts. Okay, in the end of my talk, I want to discuss further topics which may or may not come onto the table if you are performing permutation inference. And the first of these topics is the issue of multiple comparisons. So if you're analyzing brain data, you will inevitably run at some point several tests in parallel. For example, across fMRI voxels or across EEG channels. And this requires a control of the family-wise error, FWE. The FWE rate is defined as the probability of obtaining at least one false positive result from all the parallel tests you are running. And precise correction of the FWER depends on the dependency between tests, which in permutation testing is accounted for by using the same permutation across tests. So if you're choosing a random subset of all the possible permutations, it has to be the same in all the voxels or channels which you apply the analysis to. So let's say that Tij is the test statistic calculated from voxel J using permutation I. Then if you would like to test whether there's an effect somewhere in the brain, thereby rejecting what is usually called the omnibus null hypothesis or the global null hypothesis, you would use the maximum statistic. The maximum statistic is for each permutation the maximum across all voxels. And the omnibus p-value would then be given as the rank of the maximum statistic calculated from the original data within all maximum statistics calculated from the permuted data. divided by the number of total permutations. If, in contrast to that, you want to test whether there's an effect in voxel J, and this test should be corrected for multiple comparisons, then the p-value for voxel J would be given as the rank of the test statistic calculated from the non-permuted data in this voxel within the set of all maximum statistics, again divided by the number of total permutations. So the way we have described permutation tests so far, using our formal procedure and our definition of exchangeability, it can be seen that there are two core principles underlying this permutation inference idea. The first one is that you have to find a group of transformations under which the null distribution is invariant. This also includes the neutral permutation, the neutral transformation, leaving the dataset unchanged. Secondly, the test statistic has to be computed from the data after each transformation has been applied. And framed this way, permutation is just a special case of transformation, and exchangeability is just a special case of invariance. What I mean by group of transformations here is that the combination of two transformations is again another transformation. And permutation is actually a very nice example for this, because if you are combining two permutations, so permuting the data and then permuting it once again, you end up with another permutation. A very elegant example for this non-permutation based transformations is the non-parametric analog to the one sample t-test, which is called the sign flip test. Because in the univariate, in the one sample t-test, there are no two samples between values can be exchanged. So the solution is instead to apply a sign flip to the data points, which again refers to the null hypothesis. Because under the null hypothesis, the data are symmetric around zero, so that flipping the sign of your data points does not change the joint distribution of the data, which however is the case if the null hypothesis is not true. And this is exactly what we're trying to exploit in permutation tests. We want to see how extreme the exchangeability is violated in the original dataset compared with all possible permutations of the original dataset. A second example for a non-permutation based transformation that may be considered as a generalization of permutation tests is the so-called rotation transformation used in rotation tests. This is a link to an OHBM poster that my colleague Carsten once did on this topic. And the idea is that if you have spherical data, that is, if the errors are independent and identically distributed, you may not simply exchange x1 and x2, but you can also rotate the data, leading to the same joint distribution of the data. And as you can see here in the bottom example, if the null hypothesis is not true, then this rotation transformation does not preserve the joint distribution and therefore violates the generalized principle of exchangeability. Finally, this is a list of further reading. My colleague Carsten particularly recommends the first one, the paper by Ernst, Permutation Methods, a Basis for Exact Inference. With that, I would like to thank you and hopefully see you again next year. Bye bye.